Evaluate the integral of 1 over the root of x squared plus 6x from 1 to 2. This is not in a form where we can use a trig substitution on. It's not a u substitution either at this point. And so what we can do is use algebra to put it into the correct form. The way we go about doing that is to complete the square. The trig substitutions have the difference of squares or the sum of squares usually underneath a radical symbol, and so we don't have that there. With the presence of this x, that takes that away from us. But we can complete the square to make it end up as the sum of squares or difference of squares. Let's execute that. We're going to add and subtract something so we have a perfect square. The something that we need to add and subtract comes from a relationship between the coefficient on x and the number that's going to be in the perfect square. The number in the perfect square is half of the coefficient on x. So it'll be a 3. We then square that 3 to get the constant of 9. And so x squared plus 6x plus 9 will give you this perfect square of x plus 3 quantity squared. But you can't just add 9. That would change the equation. Either you take it away from the same side or you go to the other side and you add it there too. So we're going to take it away from the same side, making sure that we have the original back. Use the one 9 to be part of this root, and the other 9 will be end up being subtracted like this. And so now we know how to rewrite x squared plus 6x. It's going to be x plus 3 quantity squared minus 9. This will take the place of that underneath the root. It's not quite ready to do u sub yet. In u sub, we're looking for something simple like an x squared plus a 9. And so what we're going to do is a substitution. Unfortunately, we're going to use the letter u. But anyway, let u be x plus 3. Then du is dx. And so we'll be looking at the integral of 1 over u squared minus 9 underneath the root, that is. But it's actually a good idea to limit switch because we have x's, then we're going to have u's, and then we're going to have thetas later. So let's go ahead and limit switch. And it's a simple switch because we go to the substitution, which was u is x plus 3, and we plug in the x bounds of 2 and 1. If x is 2, then u is just 5 because you add 3 to it. If x is 1, then u is just 4 because you add 3 to it in your substitution. So here's the integral we're going to deal with for the rest of the problem, and not have to go back into x. We're going to deal with the integral from 4 to 5 of 1 over the square root of u squared minus 9. This guy is ready to have u sub trig substitution used on it. And just we have u playing a role of x. If we can handle that, we'll be fine. So we need to make sure we pick the correct trig substitution and pick the correct value of a. We normally say that we have x squared minus a squared. Here we have u squared minus a squared. And it's underneath a root. The value of a is 3. And normally we would say let x equal 3, in this case secant theta. But in this case we're going to say let u be 3 secant theta. With this substitution, we can trade our integral in to be one that's only in theta, and we actually end up in a doable integral in theta. We need to recognize what needs to be subbed for, and we need to plug in the substitution to make sure that we can get those expressions in terms of theta. There are two terms, one in the numerator, du, one in the denominator, the root of u squared minus 9. These are the two guys we need to sub for. If our substitution is u is equal to 3 secant theta, then du is going to be 3 secant theta tan theta, d theta. If our root is u squared minus 9, and we have this u is 3 secant theta substitution, automatically that root will become 3 tan theta. With the caveat, so long as u is greater than 3. And it is. Look at our limits of integration. Then that root becomes 3 tan theta. Had u been less than negative 3, then that root actually would end up as negative 3 tan theta. It's the nature of arcsecant that causes this. And so anyway, now we know what the root becomes. Because u is greater than 3, the root just becomes 3 tan theta. You could plug in the substitution, you still be at some point where you have to take an absolute value and you have to be careful. But for u greater than 3, it's just 3 tan theta. You can drop the absolute value. So we have our numerator, we have our denominator. We are ready to go. Let's plug back in and then actually perform the integration. The numerator is 3 secant theta tan theta, and d theta, and the denominator is 3 tan theta. So we get to cancel the 3's, the tan thetas, and we're just left with secant theta, d theta. This isn't an integral that you're supposed to do on the fly and figure it out. This is something either you have memorized or you have some kind of sheet to refer to. The function that has secant theta as its derivative is the natural log of the absolute value of the secant of theta plus tan theta. And it's at this point we need to make up our mind, do we want to do a limit switch? My advice always is to take a peek down the road of the limit switch. Try it out. As long as you get regular angles from the unit circle, you should be okay. Turns out that it doesn't work here though. We're going to take these u bounds, 4 and 5, and try to switch them into theta bounds. If we have the substitution, u is 3 secant theta, and we have this upper bound of u equals 5, then we have the equation that 5 is 3 secant theta. That's not one of our recognizable angles that we normally have on the unit circle. It says that the secant of theta is 5/3. We don't know theta. In fact, theta is actually the arcsecant of 5/3. Something that's going to be difficult to deal with in the problem. So we abandon this. We don't do the limit switch in this case when we get angles that really aren't on a unit circle. We're going to abandon that and go down the road of maybe trying to take a look at the triangle. This is a strange problem though, where we can get by without the triangle even. It's very rare that you're going to have the terms that are in your after integrating, the terms that you are left with are actually terms that you encountered along the way. Because of our substitution, u is 3 secant theta, we can know what secant theta is. Because of our substitution, the root of u squared minus 9 was rewritten as 3 tan theta. We can exploit these and just solve for the trig. Solve for secant theta. You get u over 3. Solve for tangent theta. You get the root of u squared minus 9 all over 3. And these guys now replace what's inside the absolute value. They will be added. U over 3 plus this root of u squared minus 9 over 3. And now we're back in u, and we can use the u numbers of 4 and 5 and finish this problem out. So that original problem, now we know the antiderivative of it. Now we're going to plug a 5 in and get 5/3 and then the root of 25 minus 9 over 3. The natural log of that. Plug a 4 in. Get 4/3, the natural log of a 4/3 plus the square root of 16 minus 9 all over 3. And let's do as much combining as we can. It turns out that, you know, the 25 minus 9 is a 16 and the square root of 16 is a 4. So that works out nice. But the 16 minus 9 is a 7, so the square root of 7 doesn't work out so nice. So that's okay. We can just leave it like that. And there's probably one more step we should take. Just because we have 5/3 and 4/3, how nicely that came out as 9/3. Then we can call this the natural log of 3. On the other side here, these are both over 3. So we could make it all over 3. And we could actually combine these two logs together if we felt like it. I'm happy with this answer though. You've gone far to get that. Let's stop right there. That would be the answer to the question.